Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. El-Moursy again in lecture number 22, part 2, which is actually through which we will only cover uh, uh, one example, or actually we will modify the example that we have started our chapter 4 with it, and we wanted to change it a little bit and see how this may change our solution. Why we are doing that? Because I want to highlight a very important concept that I have promised before to cover it, and I want to keep my promise. If you still remember the example that we have started in this chapter with, was about the what we call the game that is called light the bulb, not the buzzer. Do you still remember that? In this game that we have fully designed using all the standard way of design steps, block diagram, TT, K-maps, equations, implementation, two-level NAND, and so on, okay? We want to play a little bit with the wording of the problem. Remember, this problem has four inputs, which are representing the four chairs, and two outputs, which are the light bulb and the buzzer. By changing the parameters of the problem a little bit, I may change significantly the solution to make it a little bit maybe simpler and reflect a different style or class of problems that we need to cover, that they are very common in our life and in the problems for that chapter. So I will change the example light bulb, not buzzer. In that example, I will only change the way that the light bulb and the buzzer are changed, their outputs based on the chairs. I still have four chairs. I have four chairs. Light bulb, which we call it L, will go on if number of students sit on chairs is equal or below 2. The buzzer will go on if the number of the students sitting on the chairs equal or less, or larger than 2. Making this small change in the problem may allow me to change the solution significantly. Why is that? Although I have four chairs, I can solve the problem without having the chairs as my input. Why is that? Because actually now the light bulb and the buzzer, the two outputs, are not changing based on the position of the students sitting next to each other. I changed that. Both the outputs of the problem now are changing based on the number of the students sitting on the chair. So if I'm imagining that I have the four chairs, I may have some circuits here we will talk about this a little bit, that actually converting the chairs, the students sitting on the chairs, into, يبقى هنا the chairs themselves, the chairs here are an input. The output of this circuit will be the number of students sit on the chairs. This is a drastic change in the problem, because right now, if I'm producing this output, okay, I can use this as the input for the circuit that controls my outputs, light bulb and the buzzer. The output coming from this circuit will need how many bits? I draw them as 3, but is this really 3? I have to think. So this is a circuit that has inputs, has 4 inputs, and the output should indicate the number of the students sitting on the chairs. If I have 4 chairs, what is the range of values for the chairs in decimal? I may have 0 students, 1, 2, 3, and 4. So I have for total 5 options. Now I need to change those 5 options for the number of students sitting on the chairs, which is the output of the circuit. Okay? So the output of this circuit is the number of students sitting on the chairs. The output here has range from 0 till 4 with 5 different options. How many bits for this circuit? يبقى دي count this circuit كنا count ايه؟ Count the sitting students. Could be the name of this circuit. Okay? What is the output of this circuit? The output of this circuit is a number that represents the number of the students sitting on the chair. These are the chairs themselves. So 1 and 0 here indicates whether one student sitting or not sitting. But the output that will come here will be just the number in binary that is equivalent to, in decimal, of the number of the students sitting on the chairs. Number of students sitting on the chair could be 0, could be 1, could be 2, could be 3, could be 4. So decimal, the range of numbers here from 0 till 4. How can I convert this to binary? How many bits? Can I use 1 bit? 1 bit will give me from 0 till 1. Can I use 2 bits? 2 bits will give me from 0 till 3. Can I use 3 bits? Yes. 3 bits will give me the range of values from 0 till 7. So I have to use at least 3 bits as the output here, and I will call them N0, N1, and N2. So N here, the output is representing the number of students sitting on the chairs. Fine. Now we have 2 circuits. We have this circuit that actually is converting these chairs, the students sitting on the chairs, from a unique, distinct values to a number, and the circuit that actually this is new light bulb, not the buzzer. Okay, so let's talk about the design for each of those circuits. The first circuit here, what it's actually doing? It's actually adding the values of those chairs. Chairs will have value either 0 or 1. So it's actually accumulatively adding those values together. So I can call it it's a circuit that adds 4 inputs or bits together. This is kind of an adder circuit that adds, so we learned the half adder that adds 2 bits together. We learned the full adder that adds 3 bits together. This is neither adder, neither half adder, nor full adder. It's a circuit that adds 4 bits together. Okay, so it could be an adder. or we can also view it as an encoder because it's actually converting unique inputs into a number. Okay, whatever you call it. So we can design this, and this is homework. Design the circuit. More important than this circuit, this is the homework for you, is this circuit. I need to design for the new light bulb buzzer circuit. Right now, the circuit has a completely different set of inputs. It has an input of a different format. The input automatically representing the number of students sitting on the chairs. So, can I design this in a standard way? Yes, I can. What is my first step? Definitely it is TT. Can I build a TT for that? Yes, I can. Inputs, outputs, correct? So the inputs for the circuit will be as follows. The inputs here are, how many inputs? I have actually 3 inputs. In, out, and I still have 2 outs. So the input here will be N0, N1, N2, and this is the designator. Now the designator is directly indicates the designator represents what? Designator represents the number of students on chairs. Light bulb, not the buzzer. How many rows? Correct answer. The number of rows are 8 because I have 3 inputs. So I have 8 rows. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 2, 3, 4, 5, 6, and 7. Now the designator represents the number of students sitting on the chairs. So I can directly, based on the definition of the problem, if the number of students sitting on chairs is 2 or below, okay, L will be 1. Like 0, 1, 1, 1, 2, 1. 3 students will be 0, based on the light definition. Type 4 students sitting on the chairs will be 0. So what about 5 students sitting on the chairs? Can you ever have 5 students sitting on those chairs? The answer is definitely no. It is impossible to happen. Actually, I have only 4 chairs. So that means it's impossible for that input n number, n0, n1, n2, to have any value beyond the 4. The only permissible range of values for n is from 0 till 4, because this adder will add those bits and will give me either 0, 1, 2, 3, till from 0 through A through 4. It can never give me the value 5 or 6 or 7. Aha! This is actually what Dr. Ali have actually mentioned before. If I have impossible combination of inputs for a circuit, how can I represent the output? Do you really care about the bulb to be light on or off, the buzzer to be on or off for any combination of n beyond the 4? This is impossible combination for the inputs. That means they should be represented for the outputs as don't care. So this is a practical example for the don't cares. As Dr. Ali promised that he, in chapter 3, will learn how to deal with the don't care, okay, on the K-map and to use it. And now we will learn from where in the real life that we can get a case for don't care. Okay? Agree? Make sense? Now for the buzzer, it's two or more. That means 0, 0, 1, 1, 1, and don't cares elsewhere. This is a practical example when the don't care can occur for me in the problem. Now, your second homework is to solve the problem from, we will need the TT, from the TT, get the K-maps, okay? Right now the K-maps will be simpler because these will be a 3-variable K-map instead of 4-variable K-maps with the don't cares, okay? Put the K-maps, simplify them, get the equations and get the circuit and solve the rest of the problem as your second homework. So homework for you is to do this, the homework number 1, and this is homework number 2. Okay? Agree? So I give you a practical example for the don't care in chapter 4 as I promised to you. And now this is the last thing I will give in chapter 4, inshallah, in the next lecture, lecture number 23. We will start chapter number 5, the sequential circuits. Thank you and see you inshallah in chapter number 5.